All right, so where are we now? Last week, we set up our framework for statistical learning. Input spaces, output spaces, action spaces, hypothesis spaces, and we proposed basically a method for doing machine learning, empirical risk minimization. This was finding a prediction function that minimizes the average loss on a training set, and then we talked about the issues of overfitting. If we're searching for the function that minimizes the empirical risk over all functions, we overfit. We said, okay, let's instead constrain the set of functions we're searching over, constrain the hypothesis space to some set containing functions that we think have properties we like or are simpler, or it's just a smaller set. And this could help control overfitting. And today what we're going to do is move more strongly into this issue of preventing overfitting with what's called regularization. So regularization has various definitions depending on the context. But in machine learning these days, I think people use it rather loosely to mean anything you do to the process of fitting your data that makes your prediction function fit the training data less well, in the hopes that it's going to fit new data better. So it's going to generalize better. So very generically, that's how we could think of regularization. Fitting data less well so that it generalizes with the intent to have it generalize better. So today we're going to talk about the two most common forms of regularization, L1 and L2 regularization. And what's great is that with just these two forms of regularization, we're going to get what I think are the two most important methods of machine learning, namely ridge regression and lasso regression. So we get them right off the bat, the two biggest bang for your buck ML algorithms. And we're going to go pretty deep into these algorithms. We're going to figure out how to actually implement them. We're going to think about their properties from a math perspective with purely a practical eye. Like, what is this telling us about using these things in practice? So we've spoken about bigger and smaller hypothesis spaces. And often it's very convenient to think about nested hypothesis spaces. Nested hypothesis spaces are where we have one hypothesis space, one set of prediction functions, completely contained in a larger one. So an example, polynomials give a good example. We have all the polynomials of degree 2, and then polynomials of degree 3 contain the polynomials of degree 2, because we can just set the highest degree monomial to have a coefficient of 0. And we can write that like this. So here we have F1 is completely contained in F2, completely contained in Fn, et cetera. So these are hypothesis spaces getting larger and larger, each one containing the previous one. So polynomial functions I mentioned is one example. So one way to get these nested hypothesis spaces is to introduce a complexity measure on the individual prediction functions, the individual decision functions. So a few examples. One would be, for instance, in a linear model, the number of features you have, right? The more features you have, the more, that is, the dimension of your input space. As that increases, you could potentially have a more complicated prediction function. We'll talk about decision trees later. A decision tree, you can measure complexity with the depth of the decision tree or the number of leaf nodes, different methods, the degree of a polynomial. How about for this linear decision function? So the input is x. It maps to some linear combination of the components of the input vector x. How might we measure how might we give a complexity measure for such a function, such a prediction function? Well, I mean, one thing you could do is look at the coefficients, the w's, and kind of score them in some way. So simplest way is called L0 complexity. You count how many non-zero coefficients there are, right? So that'd be one simple measure of complexity. Another, it's one we'll talk about today, the L1 or lasso complexity. In this case, you take all your coefficients, W1 through WD, you sum their absolute values, that gives you a number, and that in some sense, that we'll talk about more, can be considered a complexity of that function. Now, why a larger coefficient should be more complex, that shouldn't necessarily be clear yet, but it's at least a way to assign a number to a linear prediction function, sum of squares of the coefficients. That's called the ridge complexity. We'll talk about that later today. Okay. So, given a complexity measure, mathematically we'll say it's something that takes a decision function as input and produces a number greater than or equal to 0. Right? It's going to give a number to every decision function in a hypothesis space. And now what we can do is define a set of, given an initial hypothesis space F, we can define a subset of hypotheses in that space, F sub R, where we're keeping all the hypotheses in F that have complexity less than or equal to R. All right? So that's a way to define a hypothesis space indexed by this complexity measure. So then, of course, we can go set R to many different values, 0, 1.2, 2.6, 5.4. Each one corresponds to a hypothesis space, each one bigger than the next, right? Because each one contains all the functions with this complexity or smaller. So we get these nested hypothesis spaces. And these are very convenient to use. So what we could do, for instance, if you go back to our first lecture, we're talking about kind of black box machine learning. R would be like a parameter we can tune, like a hyperparameter we can tune. So we would try empirical risk minimization over each of these hypothesis spaces. And for each, we would test the performance out of sample on a validation set. We would see which one works the best. And then we would take the prediction function that we get that works best on validation. So this type of constrained empirical, this is constrained empirical risk minimization. So we have, our objective function is the average loss on some training set. And we're searching for a function in the hypothesis space that minimizes that average loss, subject to the constraint on the complexity. We say, all right, just find the best we can do with complexity not exceeding R. And this goes by another name sometimes, Ivanov regularization. So Ivanov corresponds to this kind of constraint on the complexity of the functions. All right. So we could also write this in one line. Because we've defined notation for F sub R, which is the hypothesis space F constrained already to have functions with complexity at most R. So we could write it in one line like that. So till now, this is nothing new, really, because we're still talking about empirical risk minimization, and we're still searching over some hypothesis space, something that's not all function spaces, something that's not the set of all functions. So in some sense, nothing new here. We've just kind of structured the sequence of hypothesis spaces we're going to look through in this certain way, each one bigger than the next. But now we're going to talk about something that looks different. And we'll see if it actually is. This is called penalized empirical risk minimization. So here, we have this empirical risk, the average loss, in our objective function. But we've added a piece. We've added the complexity of the function into the objective function with some weight lambda, non-negative weight lambda. So what this means is that if we find a function that fits our data very well, so it has small empirical risk, but it has very high complexity, this objective value will be very large. And that's bad because we want to minimize, right? So in some sense, this is also keeping us from finding functions that are too complex, that have too high complexity measure, but it's a softer constraint on the complexity. And of course, the magnitude of lambda balances this trade-off between the complexity of F that we're going to end up finding and how well we fit the data, how small the empirical risk is. Right? So this is it's called the penalty form. It's also known as Tikhonov regularization. And just like we used cross-validation or validation set to choose R in the constraint form, we could do the same to choose lambda in this penalty form. Yeah. So this is kind of a new strategy. We haven't spoken about penalties yet. So this is our first slight tweak on pure constrained empirical risk minimization. So on the homework, ridge regression takes this form. All right. So I wanted to pose the question, does the penalty form actually give anything new? So what would that mean? So first of all, it looks different. If we wanted to solve this optimization problem, as an optimization problem, how do you see these two as different? So suppose f were suppose a set of all linear functions, okay, on some space. There's one big difference between these two objective functions, or the two optimization problems. You see?
So it changes shape of what you're minimizing.
Say again?
So it changes shape of what you're minimizing.
Yeah, so the function itself changes that you're minimizing, absolutely. So imagine you had some software you wanted to plug this optimization problem into. There's one thing that's missing here that we had in the other place, which is a constraint. So in the Ivanov form, we have a constraint to our optimization problem. And in the penalty form, we don't.
So you could, as you presented in the last slide at the very end, you could rewrite the constraint as just a different hypothesis space and remove the constraint too, right?
Yeah, so you could say, all right, well, anytime you're searching in a hypothesis space, you're constraining. This is true, but we can, suppose we did all linear functions, right? We can parameterize our hypothesis space so that we're searching over all vectors in RD, for instance. Whereas if we put an L1 penalty constraint, an L1 constraint where we say, all right, we look for all vectors W and RD for our linear function, except we're constraining so that the sum of the absolute values of those entries is at most 1. So it's that part that's the constraint. But you're right. In some sense, you could think of a hypothesis space as a constraint, but you always try to rewrite it in a way that is unconstrained. And for linear functions, you can do that easily. Yeah?
Can you do both?
Do what? Yes, can you do both? Can you have a constraint and a penalty? Sure, you could. Yeah. Okay. But it turns out that in a certain sense, for a lot of scenarios, this penalty and the constraint form are equivalent. So let's pop up to be a little bit more general for a second. Let's let capital L be some kind of arbitrary performance measure on a prediction function. So one example would be empirical risk, right? So we have some performance measure on the prediction functions, and we have some complexity measure omega, right? So when are the penalty and the constraint forms equivalent? What would that even mean? So I think the most important thing in practice is that when you use these, you're tuning over lambda in the penalty form or R in the constraint form, right? You're searching over all these different hypothesis spaces. And for each value of lambda, you'll get a different result to your optimization problem. And as you vary lambda, you'll get a sequence of these results. You'll get a whole, you can call it a regularization path, and we'll talk about that more later. And then similarly, as you tune your constraint R, you also get a whole collection of results, one for each R. And we'll say that these two methods are equivalent if the set of results you get by tuning R through all its possible values is equal to the set of results you get by tuning lambda through all its possible values. Right? And it turns out that for the methods we're talking about today, these two, so that would be Lasso and ridge regression, these two forms of optimization are equivalent in the sense I just described. I've left some more precise statement in the slides you could take a look at later. It turns out the conditions for equivalence you can get from Lagrangian duality theory. So that's going to be an optional homework problem. We'll step through that derivation. Okay. So let's talk linear least squares regression. That's going to be our starting point for everything new we learn. So linear models, our hypothesis space, let's start with the set of all possible linear functions from Rd to R, parameterized now by W. So I mentioned, I want to say this is unconstrained because we can view as the search for a decision function in this space is kind of an unconstrained search for W in RD. That's why I think of it as unconstrained. Okay. So the loss function is, of course, square loss. We have some training data. And here is our empirical risk minimization that we spoke about last week. So this is the objective function for least squares regression. So the issue is that this can overfit. In particular, when the dimension of the input space is very large compared to the amount of training points we have, this is prone to overfitting. And this is not at all unusual. So in natural language processing domains, for instance, you can have input dimension millions. So 1 million features would not be uncommon for an NLP task. And you may only have 10,000 documents or something. So what to do? We would overfit with this type of basic ERM. Okay. So let's do the penalty form of regularization. We take our least squares empirical risk and add this sum of squares penalty. This is the squared L2 norm of the vector W, Euclidean norm. Just the sum of the squares of those entries of the vector. And we're going to penalize in our objective function for having large L2 norm. All right? Alternatively, we could do the constraint form. So now we have just the plain empirical risk, and we're constraining that L2 norm of the vectors W to be at most R squared for some R you choose. All right? Good. So two different options, two different ways to write ridge regression. It's not necessarily clear, but one can prove that these two are equivalent in the sense I gave earlier. So we'll kind of switch between them. Yeah?
So one question. So you said that the regular form can overfit. Does this guarantee that it will not overfit?
So the question is, does this guarantee that we won't overfit? Well, I would say that as long as you penalize enough or constrain enough, you can be in a situation where overfitting is controlled. And we can see that with the extreme example. What happens if you take R to be 0? Yeah, the result can only be W equals 0, which predicts always 0, which doesn't overfit. It just doesn't fit your data at all. It underfits. So there must be some path between underfitting and overfitting that should be about right, the best you can do in linear functions. No? So this is an interesting slide that has some stuff. We're going to go through it slowly. Let's start on the top right. Let's introduce a little bit of notation. So let's call W hat R the result from doing a constrained L2 empirical risk minimization with the constraint on the L2 norm being R. So W hat R is what you get when you constrain the complexity to be at most R, right? Or the squared to be at most R squared. And so if R is infinity, then of course that's like having no constraints at all. So that would be the basic empirical risk minimization solution, the ERM solution. So we can call that W hat or W hat sub infinity, right? So both of those are the unconstrained solution. Now, what happens to the norm of W hat R? Let's work through a few examples. W hat R, when R is first of all, when R is very small, would you say you're regularizing a lot or a little? Say again?
A lot.
A lot. When R is small, you're having a very heavy constraint on the hypothesis space, and so you're regularizing a lot. You're controlling the complexity a lot. And when R is very large, like going towards infinity, you're regularizing very little. All right. Correspondingly, when R is very small, what's the norm of W hat R like? Small. It's when yes. And similarly, when R is large, the norm can be large. And one way to kind of think about how much you're regularizing is looking at the ratio of the norm of W hat R to the norm of the unconstrained solution W hat, right? Because when we're regularizing not at all, the solutions are the same. So of course, the norms of the solutions are are the same, and so the ratio of the norms is 1. And when we're regularizing quite a lot, so R is, say, very small or even going all the way to 0, the norm of the solution is 0, and the ratio of the norm of the constrained solution to the unconstrained solution is 0. So now let's move over to this plot on the left. And let's start with the x-axis. The x-axis runs from 0 to 1. And this is measuring. What we did was we took many different values of R, the complexity constraint, and we fit our ridge regression with that complexity constraint. And we have a set of data with 1, 2, 3, 4, 5 features: funding, college for, college, high school. This is for a data set where we're trying to predict crime rates in cities of the US. And we're fitting this linear model with various amounts of L2 penalty constraint. And as we vary R, we're going to get different solutions. And every solution is going to correspond to some point on the x-axis. Over here, this ratio is the norm. I'll just tell you, on the left we have, would you say we have R is 0 or R is infinity? 0, yeah. And as we move over here, we're penalizing more or less? Right, less. OK. So what each of these lines is the value of the coefficient for that feature corresponding to a particular ratio of the solutions of the penalized to the unpenalized. So you could each entry, each point on this x-axis, you could also think of as corresponding to a different regularization amount R. So at this point, we can read the coefficients of the solution to that model as the values on each of these lines for each of these features. Is that clear? So when we're regularizing quite a lot on the left, all the coefficients are 0. And as we regularize less and less, the coefficients get larger. And the total norm of the solution, sum of squares of these coefficients, grows. Until eventually, all the way on the right, we have the unconstrained solution. We have the unconstrained solution. All right. So this type of plot is called a regularization path. It's a plot of the regularization paths of the coefficients. OK. So
the y-axis is the loss?
Say again, please.
The y-axis is?
The y-axis is the value of the coefficients. So we pick an R, we fit our model with that constraint, we get coefficients, and that's what's plotted here. And the x-axis in this particular plot is for that R, the ratio of the norm of the constrained solution to the norm of the unconstrained solution. This is just to make the scale conveniently between 0 and 1.
But if we plot the real loss.
The real loss?
Every case is the optimal solution under that constraint. Yeah. Which means it will have another curve like decreasing. OK,
great question. Or great comment. So as we go from heavy regularization to no regularization, what happens to the empirical risk, right, on the training data? Is it large or small over here? Large. Large, because we're always predicting 0, because all of our coefficients are 0. Whereas here, it's minimized. So if we were to plot the empirical risk as a function of this, it would decrease, right? All right. OK. So this is the most important machine learning algorithm, in my opinion. And we'll discuss some more why. But the second most important is lasso regression. So I call this the second major workhorse of modern data science. So the only thing that changes is our complexity measure goes from the L2 complexity to L1. Right? So instead of sum of squares, we're doing sum of absolute values of the coefficients, the L1 norm. Of course, we have the constraint form as well, the Ivanov form. And let's look at the same regularization paths for the L1 and see what it looks like. Same problem. All right, quite different characteristic. What we see here is that these paths, they stay 0 for some time, and then each feature eventually leaves, becomes non-zero. But this characteristic of the features, of the coefficients staying 0 for heavy amounts of regularization, that's the thing that people find most appealing about Lasso. And what this leads to is people call it sparse prediction functions, where the coefficient vector may be mostly zeros. And there's some reasons this might be appealing that we'll discuss in a minute. But I just wanted to put the Lasso and the ridge regression paths, regularization paths side by side for a second. All right. So the shapes are similar, but definitely different characteristic. Okay. Comment, question? Yeah.
The right limits should be the same on both plots, right?
The right limits? Oh, in other words, the values of the coefficients should be the same on, that's right, because all the way on the right we're not regularizing, and then the objective functions should be exactly the same for Lasso and ridge. Yes, great.
And for any power for regularization of third, fourth, and so on.
Yeah, if we could change our complexity measure, and in the sense that if at the right end of the complexity measure we're not regularizing at all, then they should all be the same. Yeah, but in between they would differ. Yeah.
So
When would you use one or the other? Yeah, great question. That is something that we will be talking about a lot today. Yeah. So people get excited about this Lasso gives sparsity thing. So if the coefficients are 0, then we don't need the features that correspond to that coefficient. We could just drop that dimension of the input vector. So what's the gain? What do you guys think advantages of this would be? Why would someone be interested in this? Yeah? Say again? Interpretability. So if you started with 100 features and using Lasso, you find a prediction function that only has non-zero coefficients on 5 of them, you have a much better chance of interpreting your model. Great. I agree. Let's go. Yeah?
Does it help with performance?
Does it help with performance? That's a good question. So the answer is sometimes maybe.
Manipulating sparse matrices, usually.
Oh, you mean performance of finding the solution?
Yes. So
You use different methods to find the solution that we'll talk about later today. I would not say that people use L1 regularization because it's faster than L2 regularization. I would not say that's the case. You think it'd be faster?
L2 should be faster.
Yeah, I think L2 is typically faster.
For linear models, some of it's
but is it possible to avoid that matrices are sparse?
Say it again, please.
Is it possible to use somehow?
So in the implementation, can you use sparse matrices? So the issue is that you're going to tune your regularization parameter, most likely. And so you often want to run over the full range of the regularization parameter. So you bring it all the way from sparse to not sparse. Because you want to, I mean, it depends on your goal, but often you want to get the best performance, or at least see what the best performance is. And so you kind of run over the whole range. And so you'd start with sparse, but you'd end with not sparse solutions, and you kind of compare them.
But I guess if you use Lasso, you might have a prediction function that's more efficient because you only have to look at a subset of the features.
Okay. So you might have a more efficient prediction function because you only have to touch, say, 5 features instead of 100 or 1,000. Uh-huh. Yeah. A question, Joy.
Yeah, I have a question. That's when you are going to reduce, basically you are doing a feature reductions, right? You are reducing the features over here.
Yes. So you could think of this as a way to select features. Yeah.
To select features. So does it help to also eliminate the correlated features? Maybe unnecessarily you are using 5 different features. They are correlated instead of 5. You can just use 1.
So you're suggesting essentially in additional method to help you select features, which is find ones that are correlated and drop the correlated ones. You know what? We're going to talk about that more later today.
So I have a question. Why is it that Lasso regularization gives you sparse?
Why does Lasso give sparsity? We're going to come to that. Good question. Related to your earlier comment that it's faster, you also, when you actually deploy your model, you have to keep your features, if it's running in a real-time setting, you have to keep your features in some quick accessible storage, like RAM or something like that, or maybe SSD. And so if you have, maybe you're keeping features on, I don't know, 500 million users, and it's a lot more to have 5 features readily available on 500 million users than 1,000 features. It's just like the constraint on memory or whatever it is a lot heavier. So that would be a related cost benefit of sparsity. Sorry, yeah.
So Lasso won't be differentiable, right? Does that affect the speed of Lasso versus?
Can you say that again, please?
Lasso won't be differentiable at all points.
Lasso is not differentiable. So what your concern is, we don't necessarily know how to find the solution. We're going to come to that too. Yeah.
Does it also indicate that because we have now less feature, which means we need a smaller training set, we don't need a large training set?
So the question is, since we have fewer features, can we get by with smaller training set? But as the selection involved the full training set, so it's a little circular, I think. Yeah.
You could use a smaller chunk of data to choose your features using Lasso and then run something else on a larger set of data.
So the suggestion is use a subset of data to do your feature selection on your big set of features, and then when you find the set of features that you like, then do that on a larger set of data because it's going to be faster. Yeah, that seems like a reasonable approach if you're in a setting where running on your full data set with all your features is too time intensive. Yeah, that sounds interesting, like an interesting approach, subset. Now, in the big set of machine learning algorithms that we have access to, Lasso is one of the fastest ones. It's not as fast as Ridge, but compared to more kind of complex models like random forest and gradient boosting and things we'll come to later, neural networks, they're actually much faster. So another thing is that people will use Lasso on the full data set to do their feature selection and then take that subset of features and move that over to the slower model, but now with fewer features. Yeah, so that's a good idea as well. All right, so I put down all the ideas I had for why. So sometimes you have to, sometimes getting the features themselves is not free. Sometimes you literally buy information sources. So you could save money on buying the features. And often features are computed from other stores of data. So there's expense just to getting the features that you can do away with. All right, so everything else you guys got, great. If anyone comes up with some other ideas, let me know. I'm always looking for more reasons why sparsity is a good thing. All right. So here's the question. Why does Lasso regression give sparse solutions? Let's dig into this, and after this section, we'll take a break. All right. Let's suppose we have a very simple scenario. We have a one-dimensional input space, as we often do when we're drawing on the board. So input space is x on the x-axis. The action space and the output space are the same. Why? Reals. We're thinking about linear functions. And let's suppose we have some data. Okay. And say we do a linear fit, and it happens to nicely intersect the axes at convenient points. So let's start with a simple question. When we searched for all the linear functions, well, actually I should call them affine functions if we want to be technical, because they have intercepts, so non-zero intercepts. But anyway, as we search through all function lines, how many parameters are we searching over? 2 parameters, right? There's one way to do it is the slope and the intercept would be one way to parameterize. Okay, so our prediction function that I've drawn here by I, what is it?
Minus x plus 2.
Say again?
Minus x plus 2.
Okay. So 2 and minus x. Okay. And if we wanted to associate these with parameters, maybe we can call this one W0. And then what would W1 be? Yeah, -1. So maybe we'll put a plus here and a -1 there. And so that's W1. Right? Okay. All right, now I want to take us to another set of axes I've started drawing over here. These axes represent parameter space. Okay? So I've drawn this axis for W0 and this axis for W1. Right? So this function is represented by 2 parameters, W0 and W1, can be represented by a single point over here. What point? 2 minus 1, yeah. Okay. So any point in this space, in this parameter space, called parameter space, corresponds to a prediction function over here. Let's do one more. How about, I want to go through -1, 1. All right, so what point is that in parameter space?
-1.
Okay. -1, because the intercept is -1, and we're calling that W0, and the slope is 1. So -1, 1. Okay. So our second point in parameter space corresponds to this line. All right. So I want you guys to have this connection between prediction functions in this kind of input-output space and points in this parameter space. Right? And that every point in the parameter space corresponds to a prediction function. All right, now we can take a look at, we're building up towards the famous picture that purports to explain L1 regularization sparsity. Okay. So let's consider now a 2-dimensional input space. So instead of an intercept, I'm actually having two independent inputs, x1 and x2. And we're going to represent these sets of linear functions by a parameter space, a plane, because there's 2 parameters here. And what we've drawn here, each of these axes represents parameter space, just like over here. So every point on these axes corresponds to a linear prediction function, again, just like over here. And so what we've drawn on the left is the set of parameter values that obey this L2 constraint. The sum of the squares is R. Right? So we know from algebra 2, maybe geometry, that this expression corresponds to a circle in parameter space. Now over here, with a little bit of thinking, you can see that this L1 constraint corresponds to this diamond-shaped contour. Right? So every point on this diamond-shaped contour, it corresponds to a prediction function, right? Because these are parameters for this prediction function. And moreover, every point on this particular contour has the same L1 complexity. Now, let's look at this one some more. Which points correspond to sparse solutions?
The axis.
Yeah. Any point on the either axis has one of the coefficients 0. Because either W1 or W2 is 0. Or at the origin, they're both 0. So those are exactly corresponding to the prediction functions that have some sparsity in the parameter vector. Right? So we come now to the classic picture. Have you guys seen this before? Yes. Yes, some no. It's classic. We're going to understand it. All right, so here's the full objective function for L1 regularization. Again, with square loss. We have our empirical risk subject to this L1 constraint. Now, the blue box corresponds to all parameter vectors that obey this constraint, that the L1 norm not be larger than R. So, and remember, everything in this box corresponds to a prediction function, right? This correspondence. Right? Okay. Good, so that's the blue region. The red region, a little more complicated, and we're going to break this down. But one piece is easy, which is in the middle of all those red ellipses is a W hat. Right? W hat is our unconstrained solution. The minimizer of the empirical risk without any constraint. So the prediction function corresponding to this W hat, that's the best we can do for linear functions in terms of minimizing our average loss. So, but this does not obey our L1 constraint, so it's no good. We need we need a solution that's in the blue box, but otherwise does as well as possible minimizing the empirical risk. So we kind of need to creep from this W hat, which is the unconstrained solution, towards this constrained solution. And you can do that by thinking about these level sets of empirical risk. So what are these contours exactly? This first red ellipse corresponds to a bunch of suboptimal solutions in that they're not doing as well as the empirical risk minimizer, but they're all the same quality. These all get the exact same score in terms of this empirical risk. And as we move further and further away from W hat, the average loss, the empirical risk, gets worse. So it gets larger. The empirical risk gets larger. And we keep getting larger on these ellipses. And as soon as we first hit this blue constraint box, that's the best solution. So there's a few details here. One is, why are these ellipses? I just drew some. Why did I draw ellipses here? And the other is, yes, the picture shows ellipses hitting a corner, which is sparse, right? But why should that happen in general? So two kind of open questions here. We can rewrite this empirical risk in terms of kind of matrices and vectors, as we've talked about before. Okay. And what we can do, so I encourage you to look at this kind of at your own pace, because it's some math, and we have it as an optional homework problem in homework assignment 3, actually. But the point of this mathematics is to demonstrate that those level sets of the empirical risk, so we have the W hat, which is the empirical risk minimizer unconstrained. And as we deviate from W hat and we find things that have smaller L1 or L2 norm, we get these ellipses of W's that all have the same empirical risk. And so this demonstrates, this math basically justifies why we are drawing ellipses for the level sets of the empirical risk. So just take my word for that. Well, here's something. So one thing you guys should remember, do you see this expression? This expression? This should be hopefully familiar, and if not, maybe worth a little review, as a formula for an ellipsoid. Okay. Kind of the principal axes of the ellipsoid correspond to eigenvectors of this matrix. The eigenvalues tell you information about how kind of stretched out or versus spherical this ellipsoid is. And we'll talk a little bit more about that in a bit. All right, but to the other question, why are we hitting a corner? And here's the L2, where, proof by one example, we're not hitting a corner in this case. We're not hitting the axis in this case as the best solution, and so we're not getting something sparse. So let's just draw it out. So here's our L1 norm constraint box. And suppose W hat is right here. And one thing that we learned is that the shape of the ellipse, the eccentricity of the ellipse, is determined by this matrix X transpose X. So let's pretend that this is identity for simplicity. That's a nice spherical, it's a circle in this case. So X would be an orthogonal. If X is an orthogonal matrix, you'd have that, for example. Okay. So in that case, we get these circles, concentric circles. And for each circle that I'm drawing, the performance in terms of average loss is getting worse, but the norm of W hat is getting smaller, the L1 norm. And eventually, we're going to just hit this corner. Okay. So sparse, good. But if I started here for my W hat, will we end up at a sparse solution? Right? No. Okay, we're going to hit like right in the middle there. So the question is, do we think that we're more likely in some sense to hit a corner or a non-corner? Well, here's what I want to claim. In this case of having, say, orthogonal design matrix X, for simplicity, my claim is that if W hat is in any of these narrow segments, then when we grow that circle, we're going to hit an edge. But if it's any of these broad segments, we're going to hit a corner. I see some nods. So any of these colored segments, in the circular case, we're going to hit a corner, and anything here, we're going to hit an edge. So, convinced? Yeah.
Did this happen with the ellipsoid kind of?
Hold on 1 second, please.
So this won't happen. This might not happen with the ellipsoid kind of contours. Like
1 second, I can't hear. Please go.
So the contours, if they are an ellipse-like contours, not circular.
Okay, so this argument, of course, only pertains. This is specifically for circles, but you can work a similar argument for ellipses. And yeah, as the shape changes, you may not have this property as much. We'll look at some more examples in a bit. Okay.
So which means that because we are plotting the W's, right, in X and Y, so if the values are same, close to each other, then the chances are high, but if they are not, something like that.
Can you say it again? I think you're on to something there.
For W1 and W2, if I just consider, so if the W1 equal to W2,
Okay.
in that case, chances are.
Okay, so very interesting. So if you're, well, I thought you want to say if like the X1s, if the X's are correlated or equal or something, yeah, then things can change substantially, and we're going to look into that in the second part. Great. So funky things can happen when your input features, say the columns of X, are highly correlated or even linearly dependent. Yeah, because that makes this matrix have some very small eigenvalues when you have correlated columns, and that means some of our axes are very small, and it's not very circular at all. Yeah, we're definitely going to see that later. Great. All right, so that's the L1. This is L1 regularization. Thought it might be interesting to take just a quick look, just so you know they exist. You can take other norms, or at least they're norms if Q is bigger than 1. Otherwise, it's just a complexity penalty. And here's the contours for different values of Q. So here's our L1 and our L2, and they change shape. And so if you looked at like 0.5, for instance, or this cue ball with q less than 1, so now we're even more likely to get something that's sparse, right? So this is kind of cool if you're after sparsity, but solving the problem becomes more challenging because we have now a non-convex constraint set, which is more difficult to work with. Okay. All right. So I just want to. Well, this is the last thing before the break. I was trying to find illustrations of this famous picture, and I came across this thing in Quora. Someone asked the question, why is L1 regularization supposed to give more sparsity than L2 regularization? And they had this picture. And so my question to you, you don't have to answer it now. We're going to come to it later. But does this picture make any sense? Is there any interpretation that's connecting this picture to our discussion? Yeah?
Consider a small neighborhood of the like very small portion of any kind of a curve like ellipse, then that would be an approximation like a straight line.
Okay, so you're saying if my understanding of what you're saying is, imagine our ellipse is super large, and so when you zoom into this part, it looks almost linear. Okay. That was my first interpretation as well. That was my best guess first as well, but there's one that's even better. All right, so where are we? So we've defined the Lasso regression and the ridge regression problem, and we've explored why Lasso regression ends up sparse, and we've talked about why sparse is potentially interesting. All right, let's dig into how one actually finds this Lasso solution, because there's a bit of an issue. This is the objective function, and the issue is that the method that we've used so far for optimizing objective functions is gradient-based, gradient descent or stochastic gradient descent. But this L1 norm, not differentiable. Absolute value is not differentiable. It's not differentiable at 0, right? So what to do? What to do? That is what we're going to be talking about for the next half hour or so. All right. So first, it's a bit of a trick that we're going to use. Starts out as a trick, but then one just gets used to it as an interesting technique. It's called splitting a number into positive and negative parts. All right. So rather than giving you a formal math definition, it's very easy. So I'll just illustrate by 4 examples, and then I bet you'll know what it is. So if x is 7, the positive part of x is 7, and the negative part is 0. Positive and negative parts are denoted by x plus and x minus. All right, if x is negative 5, positive part is 0, negative part is 5. All right. If x is 0, they're both 0. All right, so let's see how we do. If x is 3, what's the positive part of 3? Yeah, and the negative part? Very good. And negative 7, positive part? 0. And negative part? Great. All right. So if I want to write x in terms of x plus and x minus, how do I do that? X plus, x is x plus minus x minus. Yeah. All right. Absolute value of x? Good. X plus x minus. All right, so the absolute value is x plus plus x minus. X is x plus plus x minus. Minus x minus. Great. OK. So let's make these substitutions in our Lasso objective and see what happens. OK. So what if we replace every entry, W is a vector. We replace every entry Wi by Wi plus minus Wi minus. So now we can think of it as 2 vectors, a W plus vector and a W minus vector. The W vector we're after is the difference W plus minus W minus. And what we're going to show is that if we make that substitution, then this optimization problem is equivalent to the original one. All right. So we've replaced every W with W plus minus W minus. So as an optimization problem, how does it compare? How many, first, variables are we optimizing over here? If we think about individual scalars. D, right. And here? Right, 2D. Any constraints here in our optimization?
Probably plus and W minus.
Okay. No, but this here, just this, there's no W plus yet. In the original formulation, any constraints? No constraints. And this one? Yes, the constraints you said. W plus and W minus are non-negative. Great. Okay, so as optimization problems, they're a little bit different, but we claim that in a certain sense they're equivalent. This is the type of thing that, this is the type of math that's often best done alone at your own pace, looking at something patiently. And for that reason, we have some notes sheets that we sent out earlier that you can work through. But we're, in any case, going to try to go through it now. And if it's still puzzling, you can go back to the notes where we break it down a little bit more slowly or a little bit differently. Okay. So first of all, if we believe that this is equivalent in a certain sense, are we done? Is this good? Is this something that we can now handle? So is it differentiable? Is the objective function differentiable?
Yes, it is.
Yes, it is. Yes, it is.
To what, I guess, is the question.
So good. So differentiable with respect to what? So it's differentiable with respect to every entry of W plus and every entry of W minus. Right? So it has a gradient with respect to kind of W plus and W minus together. Yeah?
Don't we also have another constraint that Wi plus and Wi minus can't be non-zero at the same time?
So what we'll show is that, so you're saying, shouldn't we also have an additional constraint that Wi plus and Wi minus should not both be non-zero at the same time, these sorts of things. And what we'll find is that those will arise naturally as a result of this optimization. So the W plus and W minus will have that property without explicitly requiring it in the constraints.
So what you're saying is that while our space over which we are optimizing is bigger, the optimal value will be in the same space as in the previous problem.
I'm saying that the result that we get, so we plug this into a optimization algorithm. So suppose we want to plug this in somewhere. We have to know what type of optimization algorithm to use, and I'm going to tell you that this is a quadratic program. What makes it a quadratic program? We have a objective function that's quadratic. It's convex and quadratic. The constraints are all linear. They're rather simple linear constraints. And so if you Google kind of quadratic program solver, you'll find a lot, and you could plug this in directly. And when you plug it in, you're going to get a solution. And the solution will be 2D numbers, right? There's going to be the optimal solution for W plus and W minus. Okay, and so then your question is, well, how does this relate to the original solution, which is just W? And how would you answer that? What would your guess be? What's W, given the solution W plus and W minus? Yeah, so you'd say W equal to W plus minus W minus. And then, so did you have an additional concern that you might end up with W pluses and W minuses that don't, they might not have either of them being 0 for a particular I or something? And what I claim is that that's not going to happen. And in any case, even if it did happen, the W you get would still be the same. Do you think this equivalence is obvious?
That basically means this is not unique. This split is not unique.
Well, is the split unique? Okay. So I didn't say anything precise about this split, but yet you guys knew what to do when I put in -7. You said 0, 7. You could have said, what if you'd said, 1, what?
2 and 9.
Sure. 2 and 9. So that would have been the wrong answer, and then I would have had to get all mathematical on you. All right. So let's precisely divide W plus and W minus. So the positive part is exactly if the number is non-negative, then it's the number itself. If the number is negative, then it's the negative of the number. Right? So study this for a moment. and convince yourself that exactly one of these is 0 for any given value of a. Do you know this notation? This notation says, this is called an indicator function. It evaluates to 1 if what's inside the parentheses is true and 0 otherwise. All right, let's talk about this ambiguity of the sum, because this will come up in any case in a moment. So what were we talking about? X is a -7. All right, so give me some, instead of x plus and x minus, let's call them a and b so that we don't clash with this definition. So give me some a's and b's such that the difference is -7. -7 and 0. So that we want x equal to a minus b. And then there was another one you had. 2 and 9. Great. All right, let's make another column.
But we want to do a minus b, right?
Yes, 7x, which is -7, should be equal to, oh, thank you. Should be a minus b. Good, thank you. OK. Let's look at the L1 norm of, let's look at absolute value of a plus absolute value of b. For this one, it's, OK. This one, OK. What do you think would be a representation of x in terms of a and b like this that has minimum sum of absolute value of a plus absolute value of b? Yeah? One of them 0. Say again? One of them has to be 0. Yes. Right.
And the right one has to be 0, so a has to be 0. And b has to be 0. Well, if you like a, b.
So this is, what I wrote here is so this whole thing is with the additional constraint that a is greater than or equal to 0. So b is greater than or equal to 0. So what I wrote here was not right. 0, 7. Thank you. All right, there we go. OK, thanks. OK. All right, so I think we'll come back to this in a moment. All right, so we have our positive and negative parts. The claim is that this is equivalent, but it may or may not be obvious. Let's break it down into some steps. OK. So I claim, all right, so there's one point of confusion that you might have that I wanted to get to right away. So if we take this quadratic program and plug it into a QP solver, it just sees 2D variables it's optimizing over. It has no idea that we've written W plus for some of them and W minus for others. So it doesn't know that we want W plus and W minus to be positive and negative parts. So this somehow has to work in some general sense. And so because of that, what I'm going to do is rewrite, instead of W plus and W minus, let's write with A's and B's, right? So that we're not even distracted by W plus and W minus. OK. So I claim that this problem is trivially equivalent to the original one. So we start with a minimum over W, just like we do for Lasso. And then we add in these two new variables, A and B. But we immediately constrain them. And the intent is that A minus B is W, right? And we immediately constrain them to be exactly what we want them to be for positive and negative parts. So A minus B is W. So here we have A minus B. That's where W was before. And that A plus B is the absolute value of W. And that is exactly where absolute value of W was before. So I claim that as we search now over, what's the dimension of our search space here, taken literally? Say again? Yeah, 3D, because we have W is D, and A and B are each D. So this is 3D now. We've blown it up. But the constraint is really heavy. And I hope this should be clear that this is exactly equivalent to the original problem, just by trivially enforcing that A minus B and A plus B are exactly what we need them to be. All right. So what I now want to argue is that this A plus B is absolute value of W constraint. That's redundant. Let's work that through. So now we come over to this type of thing. So suppose let's suppose we have two sets of A's and B's that give the same difference for W. So we have a particular W. We found 0, 7 for A and B, and 2, 9 for A and B, right? So they have different sum of the absolute values. So only one of these 0, 7, or 2, 9 actually sums to the absolute value of W. Say W is minus 7 in our case. And so only one of these is good. But note that we have this penalty on A plus B, right? So if we have two sets of A and B which have the same difference, so this part's the same, but have different sums, we're always going to want to choose the one that's smaller because we're minimizing over this whole objective function, right? So we're going to pick the A and B, in this case, at 0, 7. In other words, the one that has the one that is actually equal to the absolute value of W. So you could do that a little bit more precisely, where you replace any proposed A and B with, you subtract off the minimum of A and B, and one of them becomes 0, and you still have the differences W, and their sum will then be absolute value of W. All right, so it's equivalent to this, and even if we dropped A plus B is absolute value of W. Okay, so then we get it's equivalent to this. And now we have another claim. We're still optimizing over 3D variables. It's annoying. But now I claim we don't need the A minus B equals W either. All right? So why am I saying that? So let's think of this as think about looping over all possible values of W first. And then for every W, we kind of search or loop through all possible values of A and B. And then we have this constraint, though, on the A and B for any given W that A minus B equals W. So we're kind of, and then also note that in our objective function, W doesn't even show up. Only A and B show up. So in some sense, W is just kind of like this auxiliary variable that we vary. And for any given value of W, it restricts our choices of A and B. But what I want to claim is that as W varies over its full range, A and B also vary over the full plane, the full set of possible values. So I'll draw a quick picture, which might help. You guys need to help me with this. So here's, let's draw some axes for A and B. And suppose we pick a W, 0. Suppose W is 0. For W equals 0, how can I draw the set of A's and B's that satisfy the constraint? So if W is 0, we need A minus B equals 0. Let me write that in a form that I like. B equals A. Very nice. OK, so B equals A is this line. Have I done that correctly? OK. So when W is 0, we get this line. What does W equal 1 look like? B equals A plus 1. Great.
A minus 1.
Yes, A minus 1. Great. OK, so for A is 0, we're at minus 1. And so it's this line. And now, proof by picture, as we vary all the W's, we're going to cover the entire plane. So this min W, min AB with A minus B equals W. We also have this constraint that A and B are non-negative, so that keeps us in this piece, in this quadrant. But I claim that we can drop the min W, and if we drop the min W and the A minus B equals W constraint, then we're optimizing over the same quadrant of A and B. And so we can drop this anything mentioning W and have the same search, the search over the same A's and B's. OK. So what we've shown is that the original optimization problem is equivalent to this optimization problem over A and B. And where at the end, we just take A minus B, and that gives us W back. How do we know? Are we still convinced that A and B have the properties we need? Yes, so we've shown already, because nothing has changed at each step. At each step, we've gotten an equivalent problem. So it's equivalent to having the constraints that A minus B equals W and A plus B is absolute value of W. So we're still in good shape that A and B are what you want them to be, even after dropping all those constraints and dropping W. Questions, puzzles?
But eventually, if you find a solution, let's say A and B, one of them is not 0.
One of them will be, at least one of them will be 0. Let's put it that way.
I mean, if one of them is 0, everything is fine. This is equivalent. It's
Yeah.
very easy to translate the problem back into W.
Yeah.
But if
One of them will always be 0.
from here, there is no guarantee.
Well, you can't see it clearly from here, but it is true because it's because of this penalty, because we're penalizing A plus B. And note the values of A and B only show up in terms of their difference and in terms of their sum. And so, I mean, essentially, this is when we went from here to here, we guaranteed that the thing here will have A plus B as absolute value of W, and in the process, we showed that one of them must be 0. But we can argue it again from here. If one of A and B were not 0, suppose neither is 0, as you say.
Yeah.
A is 2 and B is 3. Okay? I claim if you subtract 2 from each of those, and then 1 becomes 0, 1 becomes 1, this doesn't change at all. The difference is the same. And so the objective value has only improved. So it will never find something with 2 non-zeros. Okay, good. Proved it again. Yeah.
I think you may have just answered it, but when we dropped min W, I'm totally with you that the quadrant, like the space stays the same where like there's a line in quadrant 1, like regardless of having W or not. But we had previously, because of these lines, some constraint on what A and B can be together, that they fall on those lines. And by removing min W, like we could have an A and B that aren't together on one of these lines. But maybe we're okay because one's always going to be 0, and that's kind of like what you just got at.
Okay.
So you drew these lines.
Yeah, I drew the lines, true, but we were searching over all lines.
Yes.
If we were restricted, if we only said min over W equals 4,
Yeah.
then we do have a constraint, like you're saying, on A and B.
Yep.
But, like, suppose this one. But as soon as we are minimizing over all W's, there's no really constraint on the relationship between A and B because no matter where you are, there's some line that goes through it.
You can make some line that would.
Yeah.
Right. Okay. Yeah. Using just that varying W, there's some. Line.
Yeah, exactly. Yeah. You're like sweeping this line over the entire plane. All right. Question?
I was going to say another way of thinking about it, sort of from using your analogy about looping over W and then looping over A and B. If you reverse the order of those loops, the constraint on the inner loop is W equals A plus B, so it's only one. It's a single item loop.
Oh, interesting. So find an equivalent set of an equivalent constraint, and swap the order of the minimization, and then it's a more clear.
Because there's only one value of W for any given A and B that satisfies that.
Right.
Over A and B, there's only one W, and then you can drop the W.
Oh, I like it. I like it. So if we switch A and B, for any fixed A and B, we know what W has to be. And then when we loop over W, I mean, it can't. It can't loop over W because W is fixed. So W drops. Well, I like that better. Next year. That's good. Note it. Note it. So this is almost something we can solve. We haven't actually spoken about how to handle constraints, but we will in one slide, which is this. Let's go for stochastic gradient descent. This is differentiable now. We've doubled the number of variables, but it's now differentiable. Let's use our favorite method, gradient descent or stochastic gradient descent. But then we have these pesky constraints, non-negativity constraints. And what we do then is a simple tweak, which is called projected gradient descent or projected stochastic gradient descent, which is you take a step. Suppose your constraint set is it's like here, this little curve on the ground, and I try to step away from it. I project myself back to the constraint. So I find the closest point in the constraint set to where I step to. That would be projected stochastic gradient descent or projected gradient descent. In this case, it's super easy because the constraint set is just non-negativity. And so what that means is if our step takes us such that one of our entries becomes negative, we just project it back to 0. The projection in this case would mean take anything that's negative and just make it 0. So it's as simple as that. So this is one approach to optimizing Lasso after we've converted it in this way. All right. But we're going to spend most of our time on another approach, much more popular and seems to work very well in practice. It's a coordinate descent method. So let me briefly describe coordinate descent methods to you. So in gradient descent methods, we pick a direction, and it could be any direction. That is the method of steepest descent, and we move in that direction. And when we move in that direction, every entry of our W vector, if we're optimizing W, can change, right? Because we're not stepping in a direction aligned with a coordinate axis. In coordinate descent, we only change one coordinate of W at a time. So if W is a vector, we're trying to find the optimal vector. We update only one of those entries in every pass at once. And the way we do it is pretty simple. So let's take the two-dimensional case. So in the first step, I'm going to optimize my function. So remember, the function goes along the plane like this, right? And in the first step, I'm going to find the point on the line parallel to this coordinate axis. So here's one of my axes. This is say W1. And we find the point anywhere on this line. So everything else held fixed, but W1 changes. That minimizes the function. All right? There's no gradient. We somehow or another, maybe we can't, but somehow or another, if we can, coordinate descent is find the single point on this line that minimizes the function, everything else held fixed. Once we found that minimum, then we go to the next line. Now W2. We find the point on W2, everything else held fixed, anywhere as W2 varies, and we find the point that minimizes kind of that cross-section of the function. Boom, found it. All right, are we done? No, now we have to do another round, and we iterate these rounds. So now we go back to W1, and then we search. We're in a different place now. Before we were over there. Now we're in a different place, and we search this cross-section, and we find, oh, this is the best place for W1. And then we again do W2, anywhere on this line. Right? That's coordinate descent. We keep choosing a different coordinate. We optimize just that one coordinate. Everything else held fixed. That's coordinate descent. Now, there's different ways to select which coordinate you're doing next. I mean, the standard one is cyclic, so you just start at 1, go to D, and then go back to 1, and go straight through them. You can also do random, but that is the coordinate descent method. Any questions on coordinate descent? And whether it works or not, it's a different story. I'll cite a theorem in a bit. But just as far as mechanically, how it works. All right. Okay. Got it. So here it is in more algorithmic form, and the key step is right here, where we have our objective function. Every entry of W is held fixed except one of them, the jth entry. And we find the minimum argument over Wj. And then we do that for each of the coordinates. And that's kind of one pass through coordinate descent. OK. So fine. Why are we mentioning coordinate descent for Lasso? And what's amazing about Lasso is that each of those steps, each of those searches for the minimum with respect to one of the entries of the parameter vector, in Lasso, that has a closed form solution, like an explicit expression for the solution. You can solve for it, which is pretty surprising. So coordinate descent for Lasso, which is called the shooting algorithm, I'm not sure why actually, and we iterate this closed form expression for the minimum of each coordinate. It's quite fast. I'll give you this closed form expression, and we can get a little way into puzzling it out. It's a little complicated, but we can kind of reason it through. So what have we gone here? So this is our Lasso objective function, but note that we're only minimizing over one entry of w, wj. Right? So this is the coordinate descent optimization problem. The solution, so depends on this auxiliary value cj. Let's zoom into cj. Okay. So there's some notation we have to discuss here. W sub minus j. So w is the full vector w. W sub j is the one entry that we're optimizing. W sub minus j is the other d minus 1 entries of w. Right, so we have a vector, a shortened vector. We've left out the jth entry. Correspondingly, we have our data. Remember our data points x, we have n of them. And each of those data points has d. It's a vector of length d. That's our size of our input space. And we're leaving out the jth entry, the jth feature from each of those n data points. Right? So we're taking this w minus j and x without j, taking the inner product between our parameter vector leaving out the jth entry with our input vectors leaving out the jth entry. And then we're comparing that to yi, which is the thing we're trying to predict for each thing. So this expression, yi minus this inner product, you could think of that as the residual when we try to predict yi using everything except j. So we use all the features except the jth feature. We do our best prediction, and then we see how far off we are from yi, or we get the residual from yi. And it's a vector because we have a residual for every input, each of the n inputs. All right, so that's this difference. And now we have this inner product of that vector with xij. What's that? That's the vector of the jth feature across the n inputs. All right? So this, if I could summarize this, if things are properly normalized, it's kind of like looking at the correlation between the jth feature and the residual when you try to predict the output using everything except the jth feature. So it's like we did the best we could, I like to think we did the best we could without feature j, and we have some residual, and then we say, all right, how much can we help if we put feature j back in via linear correlation? Okay. That's my best explanation of what the heck Cj is. Based on the value of Cj, we get the solution to Wj hat. And one thing to note is that Wj hat is exactly 0 when Cj is in this particular region around 0. So can we talk that through, connect that with my intuitive explanation of Cj? So Cj is like, does the jth entry help, is it correlated with the residual? Can it add some additional value to the rest of the features, basically?
Correlation is very big, basically.
Say again?
If correlation is very big, it's not going to help you much. That's why it's better to zero.
No, so it's, but we're doing correlation with the residual. So you want correlation to be high, and then it will help.
Right, but if it's too small.
If it's too small, then it won't help. And exactly right, yeah, thank you. So if the correlation is close to 0, then it's not adding much to help predict the residual. And so it ends up being, that coefficient ends up being 0. So if it's not helping reduce the residual as a feature, when you add it into the rest of the features, then we just leave it out. All right, so this is kind of the algebraic argument that corresponds to our pictorial reason for. This actually gives us a little more insight into what's happening when it's 0. All right.
So you say that each step you just remove one feature?
We don't actually remove a feature. In coordinate descent, at each step we update one parameter, a parameter for one feature, coefficient of one feature. And it could end up at exactly 0 if the correlation with the residual is small, but otherwise it's non-zero. These are non-zero entries. Yeah. I don't want to go too much into technical conditions on whether coordinate descent works. I think there's classic conditions. F needs to be continuously differentiable, and kind of strictly convex in each coordinate, that actually is not good for us, right? Because our objective function is not differentiable. So this classical condition for coordinate descent doesn't suffice for Lasso, but someone has proved a refined condition, which if the objective function decomposes in a very specific way, where we kind of contain all of the nasty non-differentiable pieces into this term that decomposes on the coordinates of x additively, then it's okay. You could study this if you're interested afterwards. But just to say that there is some theoretical support that coordinate descent will actually work for a Lasso. And it doesn't always work for arbitrarily nasty functions, okay, even if convex. As long as we're talking about coordinate descent, what happens if there's no closed form? So we had this beautiful closed form solution for the minimizer of each coordinate for a Lasso problem. What if not? How are we going to find our coordinate minimizer? Do we really have to find the exact minimizer in each coordinate? Because it seems like if there's no closed form, now we're into some kind of iterative method. And that's fine. You can take some steps towards the minimum and then continue with more coordinates. And I put in a few slides and references you can look at if you like. Okay. So that's all I wanted to say about optimizing the Lasso problem. And you'll have a chance to implement this in homework. So you'll get to work this through in detail.